Welcome to this explainer. Look, if you've ever stared at a multidimensional physics problem and just felt completely overwhelmed, you're in the right place. Today, we're taking handwritten notes from top-tier physics classes and transforming them into an absolute masterclass. We're going to take vectors from these dry, boring mathematical abstractions and turn them into a highly visual problem-solving toolkit. We're literally going to change how you see forces, movements, and the physical space around us. So let's jump right in. Okay, here's our roadmap for today. First up, we've got scalars versus vectors. Then, visualizing and representing vectors. After that, we'll get into adding and subtracting them. Fourth is vector multiplication explained. And finally, we wrap it all up by conquering advanced physics problems. All right, Section 1, Scalars versus Vectors, the mathematical divide. So we have to start at the foundation, right? Understanding the difference between two completely different numerical worlds. First, you've got the simple scalar world of everyday arithmetic. Things are easy and predictable here. 2 kilograms of apples plus 2 kilograms of oranges is 4 kilograms of fruit. Simple. That's a scalar. It just has magnitude or an amount, like mass or length. But then we enter the vector world. Here, direction matters just as much as the amount. In this world, 2 plus 2 does not always equal 4. Crazy, right? But think about it. If you walk 2 miles straight north and then turn around and walk 2 miles directly south, your total displacement, like how far you actually are from where you started, is exactly 0. That's because vectors, like displacement, velocity, and force, carry a specific direction. You can't just add their numbers together. You absolutely have to obey the rules of vector addition, which is exactly what we're going to master today. Moving on to Section 2, visualizing and representing vectors, drawing the math. Now that we know direction is so essential, how do we actually represent these mathematical arrows on paper? Well, the core anatomy of a vector is actually pretty brilliant. Let's take a vector represented by the letter A. It's broken down into two distinct parts. The regular A is just the magnitude, the brute strength of the vector. But sitting right next to it is an A with a tiny little hat on it. And honestly, that little hat is everything. It holds the absolute DNA of the vector's direction. It's the magnitude multiplied by the direction. Which brings us to a massively important concept, the unit vector. Seriously, the unit vector is going to be your best friend throughout this explainer. It is the pure essence of direction, completely stripped of all magnitude. Because its magnitude is exactly 1, you can multiply any scalar number by a unit vector, and it won't change the amount at all. It literally just points that amount in a specific direction. It's basically the mathematical equivalent of pointing your finger. To really grasp this, we anchor these abstract concepts onto a 3D grid using I-hat, J-hat, and K-hat. This grounds the math in visual reality, so we can actually plot complex directional forces. Think about it. When a problem mentions a 5 Newton force, that's just a floating number. But when it says 5 Newtons I-hat, boom, it suddenly comes alive. It means 5 Newtons pushing specifically along the x-axis. By using I, J, and K for the x, y, and z axes, we can take incredibly messy 3D diagonal forces and break them down into neat, organized little components that our brains and, our calculators can actually handle. Okay, Section 3, adding and subtracting vectors, crashing arrows together. So, now that we've got our arrows perfectly defined and placed on a grid, what happens if we literally crash them together? This is where the physics gets really dynamic. Finding a resultant vector is a strictly geometric process. We're stepping entirely away from basic arithmetic to account for the specific angle separating our forces. If two forces are yanking on an object from different angles, you definitely can't just add their magnitudes. Instead, you follow a few simple steps. First, you visually line them up, either head to tail or tail to tail. Next, you find the angle between them, always making sure to pick the smaller angle when they're tail to tail. And finally, you run them through the resultant formula. This beautiful formula blends the magnitudes of both vectors with the cosine of the angle between them, which calculates the exact path the object is ultimately going to take. Now, there's a specific derivation here that is an absolute game changer. When vector A and vector B have the exact same strength, the terrifying math beautifully simplifies into a massive shortcut for complex exam problems. That huge, intimidating square root formula just collapses down to r equals 2a times the cosine of theta over 2. Literally, if you memorize this shortcut, you're going to save yourself minutes of painful calculation on a test. It's a perfect example of how recognizing mathematical patterns in vectors gives you a totally unfair advantage. Let's keep moving. Section 4, vector multiplication explained, dots and crosses. Let's continue leveling up our mathematical arsenal by looking at how to multiply vectors together. And this splits into two radically different operations. We basically got a two worlds comparison here. First, the dot product. This gives you a simple scalar number using cosine. But then you have the cross product, which mathematically creates a completely new perpendicular vector using sine. Think about how wild that is for a second. Depending on the physics application, multiplying two vectors can either strip away their direction entirely, leaving you with a plain old scalar, or it can spawn a brand new third vector pointing in a completely new direction. If forces are working together in the same direction, the dot product peaks. But if you're dealing with rotational forces, where perpendicular action is key, the cross product takes the spotlight. And figuring out exactly where that new cross product vector points is actually super intuitive thanks to the right-hand thumb rule. It gives you a physical, real-world trick so you don't have to visualize invisible 3D math in your head. You literally just take your right hand, curl your fingers from the first vector toward the second vector, and wherever your thumb points, bam, that is the direction of your new vector. There's also the cyclical IJK rule, which is a neat little trick. I crossed with J gives you K. It's a closed loop. It's this elegant little engine of physics that dictates things like magnetic fields and torque. All right, we've made it to Section 5, Conquering Advanced Physics Problems, the boss battle. Let's see how everything we've learned builds up to conquering real top-tier physics exam problems. Everything we've covered so far has been training for this. We can see our dot product in action in a recent JEE physics problem, multiplying a 3D force vector and a displacement vector to generate a clean, simple scalar answer of 40 joules of work. The problem starts with this messy array of I, J, and K components for both force and position. It looks terrible. But because calculating work requires a dot product, you simply multiply the matching components together. The I's multiply with the I's, the J's with the J's. The directional unit vectors literally vanish into the math, leaving behind 15 minus 10 plus 35, which equals exactly 40. See? This proves that once you know the rules, multidimensional physics is honestly just basic arithmetic in disguise. And it works for even tougher stuff. Take this highly intimidating JEE advanced problem, where the vectors are literally shifting over time. At first glance, seeing omegas and t's mixed into vectors a and b might totally induce a panic attack. But let's break it down. You don't need to panic, you just need to apply the magnitude formulas we've been talking about. The math reveals that the magnitude of b remains a constant a because of a really clever trigonometric identity. From there, you're just plugging values into the basic vector subtraction equation. You do the algebra, and the angle magically reveals itself to be 60 degrees. It's a huge testament to the fact that advanced physics is really just basic vector rules applied with confidence. And that brings us to a brilliant shortcut from the student notes, known as the MR Starbox trick. Understanding the geometrical boundaries of vectors lets you bypass heavy calculations completely. Imagine a multiple choice scenario asking which combination of three forces can equal 0. You don't need to do any crazy resultant math here. You literally just check if the third number can logically form a triangle with the other two. For example, forces of 3, 4, and 2 can result in 0 because 2 falls neatly in the range between 4 minus 3 and 4 plus 3. It's spatial reasoning completely triumphing over brute force calculation. So, if mastering vector mechanics can transform terrifying multidimensional forces into simple, predictable algebra, what other complex mysteries of the physical universe can this math help you unlock? Vectors really are the fundamental, directional language of the universe's mechanics. From predicting the precise orbit of satellites to understanding the invisible flow of electric currents, these simple rules of I, J, and K govern absolutely all of it. You now have the geometric framework to decode a chaotic, moving world. So the question is, what mysteries will you unlock with it next?